What is the strongest thing the universe can create? Not the hardest, not the biggest, but the most powerful engine nature can keep alive for millions of years, somewhere in the deep past. Tiny points of ancient light crossed billions of light years to reveal something almost impossible: quasars. Galaxies with dark hearts so energetic they can outshine 1,000 galaxies at once. Welcome to Boring Science Stories. Before we drift into this quiet journey through black holes, falling matter, magnetic jets, and the sleeping monster at the center of our own Milky Way, please take a moment to like, subscribe, and share this video with someone who enjoys calm science before sleep. Thank you for spending your time here. And just for curiosity, what time is it where you're watching or listening, and where in the world are you tonight? Leave a comment below. Now, let us begin our journey into the strongest engine the universe can create. The strongest things in the universe do not always announce themselves with shape. Some do not shine like ordinary stars, or spread across the sky as visible clouds, or reveal a surface that can be mapped and measured. Some begin as almost nothing to the eye, a faint point where a telescope records a signal that seems too small to carry much consequence. In the case of quasars, that first impression is deeply misleading. The point is not a star, it is not a nearby ember, it is the bright central region of a galaxy so distant that its light has spent a large fraction of cosmic history crossing expanding space. What appears compact and faint from Earth can be an engine so luminous that the rest of its host galaxy almost disappears beneath it. This is where the question of strength has to be handled carefully, because strength in the universe is not only a matter of hardness, mass, or force in a single instant. A supernova can briefly blaze with overwhelming brilliance. A neutron star can hold matter in a state denser than anything found in ordinary worlds. A black hole can bend space-time until escape becomes impossible. But a quasar introduces a different kind of power, not merely violent, but sustained. It can remain active for timescales long enough to influence an entire galaxy, long enough for its radiation and jets to cross distances that human intuition cannot easily hold, long enough for a small central region to become the regulating heart of a cosmic structure. The visible clue is small, the implication is not. A quasar is not a separate kind of star. Even though its name grew from that early confusion, it is the blazing environment around a supermassive black hole, where gas, dust, plasma, gravity, and magnetic fields are drawn into one of the most efficient engines nature can build. The black hole itself gives off no light from within its event horizon. The brightness comes from what falls toward it, from matter losing altitude in a gravitational field so deep that falling becomes a source of immense energy. Before that explanation was accepted, quasars seemed almost unreasonable. They were too bright if they were far away, and too strange if they were nearby. They looked point-like, yet they could outshine the combined starlight of their galaxies. Their signals reached radio telescopes from parts of the sky where ordinary explanations began to fail. They demanded a power source that was not simply large, but concentrated, hidden, and capable of turning matter into radiation with astonishing efficiency. That demand is what makes them central to the question. The universe can create many extreme objects, but few combine scale and focus in quite the same way. A quasar is powered from a region that may be no larger than a solar system, yet its effects can stretch far beyond the galaxy that contains it. The energy begins near the center in crowded darkness, where matter that once belonged to stars, gas clouds, or disrupted worlds loses its old identity and becomes part of a rotating disk. This disk is not calm. It is heated by compression, friction, turbulence, and the relentless difference in speed between inner and outer orbits. The closer material moves toward the black hole, the faster it must travel, and the more violently it interacts with the material around it. The gas becomes plasma, a state in which atoms are stripped into charged particles. Those particles move under the influence of magnetic fields, and the magnetic fields are twisted by rotation until the system begins to act less like a simple drain and more like a dynamo. Matter falls inward. Radiation streams outward. Some particles are caught and accelerated into narrow jets that can pierce the surrounding galaxy and continue into intergalactic space. The engine feeds, but it also resists itself. Radiation pressure can push back against incoming gas, slowing the flow, forcing the system into a balance between appetite and restraint. This balance is part of the reason quasars matter so much. They are not just explosions. They are engines with feedback, structure, and duration. Their strength is not exhausted in a single flash. It is maintained through a continuing relationship between gravity pulling matter inward and energy pushing matter away. That relationship gives quasars their almost paradoxical character. They are signs of destruction, because matter falling toward the black hole is heated, stripped, accelerated, and often lost forever. Yet they are also signs of order, because their activity follows physical limits. They are not random fires in space. They are built from the laws of motion, thermodynamics, electromagnetism, and general relativity working together under extreme conditions. The result can be so bright that it becomes visible across most of the observable universe, long before astronomers understood what quasars were. Their light had already crossed space for billions of years, carrying a record of an earlier cosmos. To observe a distant quasar is to look back toward a younger universe, when galaxies were closer together, gas was more abundant, and black holes had more opportunities to feed. In that younger era, the engines were easier to ignite. Galactic mergers stirred matter inward. Dense environments fed central black holes. The conditions that now appear rare in the nearby universe were once part of a more crowded and turbulent cosmic landscape. This is why quasars are not merely objects of power. They are historical markers. They tell a story about the growth of galaxies, the formation of structure, and the changing behavior of the universe across time. Their absence nearby is as important as their presence far away. It suggests that the universe has aged out of its most active feeding phase, at least in the local cosmic neighborhood. Most nearby giant black holes now sit comparatively quiet, surrounded by too little fuel to produce anything like the great beacons seen at high redshift. The Milky Way carries such a sleeper at its center, Sagittarius. A star is massive, dark, and real. Yet from a distance it would not look like a quasar. It is underfed. The central engine is present, but the furnace is not fully lit. This contrast sharpens the meaning of a quasar. The black hole alone is not the whole answer. Strength appears when the black hole is given matter, when the environment supplies fuel, and when that fuel organizes into a disk capable of converting gravitational fall into radiation. A quiet black hole can dominate the orbits near it without illuminating the cosmos. A feeding black hole can become a lighthouse seen across deep time. In this sense, the strongest thing the universe can create is not one object in isolation, but a system, a supermassive black hole joined to a living flow of matter. The darkness at the center provides the depth. The accretion disk provides the light. The magnetic fields provide direction, the jets provide reach. Together they form an engine able to affect regions vastly larger than itself. That reach changes how strength should be imagined. A mountain is strong because it resists. A star is strong because it shines through fusion. A black hole is strong because it traps. A quasar is strong because it transforms. It takes the gravitational energy of falling matter and turns it into radiation, heat, particle motion, and galactic consequence. It can slow the birth of stars by heating gas that might otherwise collapse. It can inflate huge bubbles of energetic particles. It can send jets into the thin medium between galaxies, carrying influence far from the event horizon that started the process. The center may be hidden, but its effects are not confined. They move outward until the galaxy around it becomes part of the engine's story. The first section of this journey therefore begins not with the black hole alone, but with the mismatch that made quasars unavoidable tiny points of light and radio emission that implied impossible strength. The old categories could not contain them. A star could not explain them. A normal galaxy could not explain them. A temporary explosion could not explain their persistence. The evidence pointed towards something compact, distant, and enduringly luminous, something whose full nature only became clear after astronomy learned to connect radio signals, red-shifted light, active galactic cores, and the physics of accretion. What once looked like a strange pinprick became a signpost to one of the deepest engines in nature. The strongest thing the universe can create may not be the thing that strikes hardest for a moment. It may be the thing that keeps working, keeps feeding, keeps shaping its surroundings long after a flash would have faded. In that quieter and more unsettling definition of strength, the quasar stands near the edge of what known physics can build a compact darkness surrounded by light, powerful enough to make galaxies seem dim. A radio antenna hears the sky differently from an eye. It does not wait for starlight to form a familiar point, or for a nebula to reveal itself as a pale stain against darkness. It listens for longer waves, for signals that can pass through dust, spill out of magnetic storms, and arrive from places where ordinary optical astronomy may see almost nothing at all. That difference quietly changed the scale of the quasar mystery before the word quasar existed. The first clues did not look like monsters. They arrived as interference, as unwanted noise in equipment built for practical communication, and then as fixed signals that returned with the turning of Earth. In the 1930s, Carl Jansky traced some of that radio noise to the direction of the Milky Way, showing that space was not silent at radio wavelengths. The discovery did not immediately overturn astronomy. It was easy to treat it as a technical curiosity, a new kind of signal from an old sky. Yet it opened a second window, and once that window widened, the universe no longer matched the neat optical picture that had been built from visible light alone. Radio astronomy grew slowly at first, then with increasing force after wartime advances in antenna design, receivers, and signal processing. The sky began to fill with sources. Some were understandable. The sun produced radio emission. Jupiter could be loud. The Crab Nebula and other remnants of stellar explosions had charged particles and magnetic fields capable of producing long-wavelength radiation. Nearby galaxies could also shine in radio, especially when something energetic disturbed their gas. But alongside these recognizable objects came a stranger population, small, intense radio sources with no obvious visible counterpart. They were points in the radio sky, compact enough to frustrate early instruments, scattered across directions where no familiar optical objects seemed to belong. Their locations could be estimated, but not always precisely enough. Their physical nature remained almost blank. The unease came from a simple fork in the reasoning. If these radio sources were close, perhaps within the Milky Way, then some kind of local star or nebula should often have appeared in visible light. If they were far away, outside the Milky Way, then their radio brightness implied a much more severe conclusion. They would have to be astonishingly powerful. Either answer was uncomfortable, but the distant answer was harder to accept because it demanded a universe with engines far beyond normal stellar output. At the time, astronomy was still adjusting to the full meaning of galaxies beyond the Milky Way. The cosmic distance scale had expanded, but the emotional and physical sense of that expansion had not fully settled. A faint optical galaxy at great distance was one thing. A compact radio source with enormous implied luminosity was another. The instruments were seeing something real, but the categories were not ready for it. This is one of the quieter lessons of the early quasar story. The mystery did not begin because astronomers lacked imagination. It began because the evidence was forcing several extreme possibilities into view at once, and none of them fit comfortably inside the known universe. Radio catalogues became maps of uncertainty. Surveys recorded sources according to their positions and strengths, giving them practical names before they had physical identities. Each entry was a clue without a solved object attached. Some sources sat near the plane of the Milky Way, where foreground gas, dust, stars, and remnants made interpretation difficult. Others appeared well away from the galactic band, where local explanations became less persuasive. The distribution mattered. A population spread broadly across the sky hinted that at least many of the sources were not merely features of the Milky Way, but a broad distribution by itself did not say what they were. It only deepened the problem. These points did not behave like ordinary stars, and they did not resemble normal galaxies in the limited data then available. Some were strong in radio but faint or invisible in optical surveys. Some seemed tied to strange galaxies whose centres were unusually bright. Others remained unresolved, almost star-like if seen at all. The radio sky was not just adding more objects. It was revealing that energy in the universe could be arranged in ways optical telescopes had missed. The physics behind radio emission also carried its own implication. Much of the strongest cosmic radio light comes from charged particles moving through magnetic fields, often at speeds close to that of light. This process, known as synchrotron radiation, does not belong to calm stellar surfaces. It points toward acceleration, turbulence, shocks, and magnetic structure. A bright radio source therefore suggests not merely a hot object, but a machine for driving particles to extreme energies. In stellar remnants, that machine could be an expanding shockwave from a supernova. In Jupiter, it could involve magnetospheric processes. But for the unexplained point sources, the scale of the machine was uncertain. If nearby, it had to be unusually hidden. If distant, it had to be powerful enough to challenge the known inventory of cosmic engines. The sky was beginning to offer not one puzzle, but a population of puzzles with similar signatures. Among the most important early sources were those whose radio emission appeared tied to galaxies with disturbed or unusually active centres. Cygnus A became one of the great examples. It was not a simple star. Its radio brightness was immense, and as radio observations improved, its structure proved to be extended and organised, with activity reaching far beyond the central visible galaxy. That meant the radio light could not be treated as a small surface glow from an ordinary object. It had architecture, it had direction, it carried energy away from a core into surrounding space. Even before the full black hole picture emerged, sources like Cygnus A showed that something in galactic centres could launch activity on scales much larger than the bright central region itself. The core was not merely shining, it was acting. This distinction would become essential later, because quasars would eventually be understood not just as bright points, but as the most intense members of a broader family of active galaxies. At first, however, the family resemblance was hidden by observational limits. A radio telescope might see lobes or jets. An optical telescope might see a faint point or a peculiar galaxy. An X-ray detector, once such instruments became available, would reveal still another face of the same kind of power. Different wavelengths gave different fragments of the animal, and the fragments did not yet assemble into a single body. The radio sources therefore occupied a strange scientific middle ground. They were measurable enough to be catalogued, but not understood well enough to be named by their cause. Their labels described appearance rather than nature radio source, quasi-stellar source, peculiar galaxy, active nucleus. Such names can be useful, but they also mark a boundary. They show where observation has outrun explanation. The most difficult part was location. In astronomy, distance changes everything. A candle nearby and a lighthouse far away can send a similar brightness to an observer, but their meanings are not remotely the same. For the radio sources, distance determined whether they were modest oddities or cosmic giants. Yet measuring distance required identifying their optical counterparts, and that required far better positions than early radio surveys could easily provide. The sky is wide, and a small uncertainty in position can contain many faint optical objects, any of which might be unrelated. Without a secure match, the spectrum could not be studied. Without a spectrum, the distance could not be known. Without the distance, the power source could not be judged. The mystery was locked not by lack of curiosity, but by the precision of the instruments. As radio techniques improved, the lock began to loosen. Interferometry, which combined signals from separated antennas to sharpen detail, allowed astronomers to narrow positions with increasing confidence. Occultations by the moon, when the moon passes in front of a radio source and temporarily blocks it, offered another way to refine a location. These methods transformed vague radio points into targets that optical telescopes could actually pursue. The shift may sound technical, but it carried enormous narrative weight. A distant engine cannot be understood until its signal is attached to a definite place in the sky. Once the positions became precise, the invisible began to acquire counterparts. A faint optical point could be placed where the radio source had been. A spectrum could be taken. Lines could be examined. The radio clues were no longer isolated sounds from the dark. They were becoming addresses. At that threshold, the quasar mystery changed form. The question was no longer only why the radio sky contained strange compact sources. It became whether those sources were nearby objects wearing a misleading disguise, or remote engines bright enough to make ordinary galaxies seem weak. The earliest radio surveys had supplied the unease. Better positioning supplied the test. What remained was for one source to be identified clearly enough that its light could reveal how far it had travelled, and in doing so force the small radio point to become something almost impossible in scale. A single radio source can change its meaning when its position becomes precise enough. 3C273 had already belonged to a catalogue before it became a doorway, one entry among many in a growing map of strange radio objects. Its signal was strong, its nature uncertain, and for a time it carried the same unresolved tension as the rest of the population. It was there, it was compact, and it was not yet understood. The decisive change came when astronomers used the moon itself as a measuring tool. As the moon passed in front of the source, its edge briefly blocked the radio emission, allowing the position to be narrowed with a sharpness that ordinary radio observations had struggled to reach. This kind of occultation did not explain the object, but it gave the mystery a fixed address. Once the address was known, an optical telescope could be pointed with confidence toward the same place, and there, in the matching patch of sky, a faint star-like point appeared. It did not look like a galaxy in any ordinary sense. It did not spread into a soft disk or show spiral arms. It looked almost too simple for the radio power associated with it. Yet the faint point and the radio source were now tied together closely enough that the next step became possible. Light could be broken into a spectrum. The spectrum could be searched for the fingerprints of atoms, and inside those fingerprints, the distance to the object could begin to reveal itself. A spectrum is one of astronomy's quietest instruments of transformation. It takes a point of light and turns it into a record of matter, motion, and history. When starlight or galactic light passes through gas, certain wavelengths are absorbed or emitted by particular elements, leaving patterns that can be recognized again and again across the universe. Hydrogen has its marks, oxygen has its marks. Other atoms carry their own signatures. These patterns are useful because they are not arbitrary. They arise from the inner structure of atoms, from the energies their electrons can absorb or release. In a nearby star, the lines fall where laboratory physics expects them to fall. In a distant galaxy, the same lines may appear shifted if they are shifted toward longer, redder wavelengths. The light has been stretched. Some of that stretching can come from motion when an object is moving away. On cosmic scales, it can also come from the expansion of space itself, which lengthens the light during its journey. For 3C273, the spectral lines were not missing, they were displaced. The challenge was recognizing them in unfamiliar positions. Martin Schmidt saw that the strange arrangement made sense if familiar lines had been shifted strongly toward the red. With that interpretation, the faint point stopped being a local curiosity. It became an object at an extraordinary distance, billions of light-years away, far beyond the range that had felt comfortable for such an intense source. The redshift did not merely add a number to a catalogue, it changed the physical category of the object. If 3C273 was really that far away, then the energy required to make it visible from Earth was enormous. A nearby object can appear bright because it is close. A distant object that appears bright must be intrinsically powerful. This is the cruel arithmetic of distance in astronomy. Light spreads as it travels. The farther it goes, the more thinly its energy is distributed across space. For a source billions of light-years away to remain detectable and bright, it cannot be ordinary. It must pour out radiation at a rate that makes normal stellar explanations collapse. 3C273 therefore became not just distant and not just bright, but bright because it was distant. Its faintness through a telescope was no longer a sign of modest energy. It was the dimmed remnant of an immense engine seen across expanding space. That distinction is what made the discovery so disruptive. The object looked star-like because it was unresolved, not because it was a star. It had once been called quasi-stellar because its optical appearance resembled a point. The name preserved the confusion. The spectrum broke it open. Once the redshift was understood, the source had to be placed in the realm of cosmology rather than the neighbourhood of the Milky Way. It belonged to a universe large enough and old enough for its light to have travelled through deep time. That was not an easy conclusion to absorb. It required trust not only in the measurement, but in the expanding universe framework that gave the redshift its distance meaning. By then, the broad structure of the Big Bang picture had begun to settle more firmly into astronomy. But quasars placed emotional and theoretical pressure on it. They were not passive markers of expansion. They were extreme objects embedded within it, bright enough to announce that the younger universe contained forms of activity far more intense than the nearby sky suggested. The first secure redshifts therefore did two things at once. They confirmed that these strange radio-linked points were remote, and they forced astronomers to admit that the distant universe was not merely filled with fainter versions of familiar objects. It had its own active population. It had engines that were common in earlier epochs and rare close to home. 3C273 became a pivot because it made that conclusion difficult to avoid. After its distance was recognized, other sources could be studied with the same suspicion. Strange spectra that had seemed unreadable could be reinterpreted as familiar lines shifted to unexpected wavelengths. More quasi-stellar sources found their places along the cosmic distance scale. The pattern strengthened. These were not isolated mistakes, nor a single exceptional case. They formed a population of compact, luminous, distant objects. Their light was old, their power was severe, and their existence meant that the universe had changed over time. That time dependence mattered deeply. If quasars were mostly found far away, then they were mostly being seen as they existed long ago. Astronomy is not only a study of distance, it is a study of delay. Light takes time to travel, so the deeper the observation reaches, the earlier the universe appears. A quasar at great distance is not being observed as it is now, in some unreachable present. It is being observed as it was when the light began its journey. The farther quasars were found, the more clearly they belonged to a younger cosmic era. The nearby universe did not show the same abundance of blazing quasar activity. The implication was not that quasars had vanished entirely from reality, but that the conditions that made them common had faded in the local cosmic present. Galaxies had aged, gas supplies had changed, mergers had become less frequent in many regions, central black holes still existed, but many had lost the steady fuel needed to become brilliant. The redshift measurements therefore turned quasars into clocks as well as lamps. They marked an era when galaxies and their central engines were more vigorously connected. The universe revealed by them was not static, it evolved. Its strongest engines had histories. Its brightness had seasons measured not in years, but in billions of years. This helped explain why early doubts were so strong. The claim was not simply that a new object had been found. The claim was that a tiny-looking point could be the dominant light of a remote galaxy, that it could shine from a time when the universe itself was younger, and that its apparent simplicity hid an energy source of astonishing density. Such a claim needed repeated support. It needed more spectra, more identifications, and better agreement between radio positions and optical counterparts. That support accumulated gradually. No single observation made every skeptic disappear. Science rarely changes by one clean break when the conclusion is this strange. Instead, the alternatives became less able to carry the evidence. Local explanations struggled to account for the redshifts, the sky distribution, the brightness, and the growing number of similar objects. The cosmological interpretation, difficult as it was, began to organize the facts more naturally. Quasars were far away. They were bright beyond ordinary galaxies. They were compact in appearance because their active central regions were too small and too distant to be resolved by ordinary telescopes. The name remained, but its meaning changed. A quasi-stellar object was not a false star so much as a galaxy's core overwhelming its own host. That realization prepared the path toward the deeper engine. Distance alone could not explain how the energy was produced. Redshift could prove scale, but not mechanism. Once quasars were placed billions of light-years away, the problem of their power became sharper, not softer. A nearby unknown object could be deferred as a local oddity. A distant luminous object demanded a physical account. Something had to be able to release more energy than a galaxy's ordinary stars from a region too small to behave like a normal galaxy. The redshift of 3C273 therefore did not solve the mystery in the comfortable sense. It removed the safer answers. It pushed quasars out of the local sky and into the deep universe, where their weakness as little points became their greatest accusation. They were not faint because they were weak. They were faint because they were almost unimaginably far away, and still strong enough to be seen. The distance to a quasar created one kind of difficulty, but its changing light created another. Once 3C273 had been placed far outside the local universe, its brightness was already hard enough to accept. A faint point had become a cosmic beacon, and the energy implied by that distance pushed well beyond the power of ordinary stars. Yet older photographic plates added a more restrictive clue. The object had not simply shone with great intensity. It had varied. Across observations separated by months and years, its brightness shifted enough to show that the source was not a steady, galaxy-sized glow smeared across a vast region. It changed on humanly measurable timescales, and in astronomy that detail matters with unusual force. A source cannot alter its whole brightness faster than information can cross it. No physical change can coordinate itself across a region faster than light. If an object brightens or dims within a certain span of time, the active region responsible for that change must fit inside the distance light can travel during that span. This is not a fragile inference. It follows from the basic limit built into relativity. A galaxy may be hundreds of thousands of light-years across, so its full starlight cannot rise and fall as one body over a single year. Too many separate stars are too far apart, and the message that something has changed cannot reach all of them at once. A compact engine can vary quickly. A vast ordinary galaxy cannot. The variability of quasars therefore tightened the mystery into a smaller space. Their brightness demanded enormous output. Their timing demanded a limited source. The universe was presenting an engine that appeared to combine the luminosity of a galaxy with the scale of something closer to a stellar system. That combination was the true wound in the early explanation. It was not enough to say quasars were bright. Many things can be bright if they are large enough. A galaxy shines because it contains immense numbers of stars, each contributing its own small share to the total. But a quasar's changing light suggested that much of its dominant energy emerged from a central region, small enough to act coherently over short times. The power was not broadly distributed, it was concentrated. This concentration turned the problem from a question of fuel into a question of mechanism. If ordinary stellar fusion were responsible, the region would need impossible numbers of stars packed together, shining at once, without spreading into the visible form of a normal galaxy. If repeated stellar explosions were responsible, the activity would have to be organized and sustained in a way explosions do not naturally provide. A supernova can briefly become extraordinary, but it is an ending, not an engine. It expands, cools, and fades. It does not remain locked in a compact state, producing regulated power for millions of years. The variability clue did not identify the correct engine by itself, but it eliminated many comfortable ones. It showed that whatever powered quasars had to be both small and efficient, able to draw intense energy from matter without requiring an impossible volume of stars. It also had to endure. Short-lived catastrophe could not explain a population of sources seen across cosmic time, many of them maintaining activity long enough to become central features of their host galaxies. This is why quasars began to press so strongly on the idea of gravity as a power source. Gravity is usually experienced as gentle at human scale, a steady pull that holds worlds and bodies in place. But in deep astrophysical settings, gravity can concentrate energy more effectively than almost anything else. Matter falling into a deep gravitational well does not simply move inward. It gives up energy as it descends. Around a compact object, especially a black hole, that surrendered energy can become heat, radiation, and accelerated particles. The smaller and deeper the well, the more extreme the conversion can become. The variability of quasars pointed toward exactly that sort of environment, because only a compact center could release such energy while changing so rapidly. The evidence was narrowing toward a dark heart before the full picture was widely accepted. A quasar looked like a point not because its true power was small, but because the active region sat unresolved at a huge distance, overwhelming the softer light of the surrounding galaxy. Behind that point there could be a host galaxy with ordinary stars, dust, and structure, but the nucleus was so bright that it dominated the observation. It was like trying to study a landscape with a searchlight aimed directly into the instrument. The source of glare did not need to fill the landscape to control the view. It only needed to outshine it. In quasars, the central engine does this on a galactic scale. A region near the black hole can pour out more light than all the stars around it, so the galaxy becomes secondary to its own core. This inversion is one of the most important features of active galaxies. In most galaxies, the stars define the system. In a quasar, the nucleus seizes the identity of the whole object. The compactness implied by variability also explained why early optical observations had been so misleading. A normal galaxy at great distance can blur into a faint patch, but a quasar's core remains concentrated enough to resemble a star. The eye of the telescope sees a point, and the name quasi-stellar preserves that first deception. Yet the spectrum and variability together reveal that the resemblance is superficial. A star is not capable of such luminosity at such distance. A normal stellar surface cannot account for the radio emission, the ultraviolet glare, the high-energy radiation, and the changes in brightness. The point-like appearance becomes not a clue of simplicity, but a clue of compression. The more astronomers examined quasars, the more the evidence insisted that power was being extracted from a small central volume, where matter was forced into an extreme state. That volume did not have to be smaller than a star in the strictest sense, but it had to be small compared with the galaxy whose light it overwhelmed. It had to be a region where velocities were high, temperatures severe, and ordinary gas transformed into plasma. It had to be a place where gravity did not merely organize orbits, but fed an energy cycle. This moved quasars away from the older idea of strange stars and toward the modern picture of active galactic nuclei. The active nucleus is not simply the black hole. The black hole is the anchor. The active region includes the matter around it, the accretion disk, the hot gas, the magnetic fields, the surrounding dust, and the channels through which particles may escape. The black hole defines the depth of the well, but the visible power appears before matter crosses the event horizon. This distinction matters because black holes themselves are dark. The light comes from the last stages of approach, from matter crowded into a rotating flow, colliding, heating, and shedding energy before some of it disappears. The compactness clue, therefore, does not point to light emerging from inside the black hole. It points to light produced by the violence of arrival. The event horizon remains a boundary, but the region just outside it becomes one of the brightest environments in nature. In this way, a quasar turns absence into evidence. The hidden center cannot be seen directly in ordinary light, yet its surroundings betray it. The brightness changes too quickly. The spectrum carries too much energy. The radio emission indicates charged particles and magnetic fields. The host galaxy is overpowered by its own core, piece by piece. The object becomes less like a star and more like a machine built around a gravitational abyss. Even the apparent contradiction begins to make sense. The source can be compact because the energy does not come from a broad surface. It comes from matter falling into a sharply curved region of space-time. It can be bright because the conversion of gravitational energy near a black hole can be far more efficient than fusion in stellar interiors. It can last because the flow of matter can continue as long as the galaxy supplies fuel. The early measurements did not yet contain the complete theory, but they had already set strict conditions. Any successful explanation had to respect distance, luminosity, variability, and duration at once. That combination made quasars more than luminous curiosities. It made them tests of what the universe can do when mass is concentrated, fuel is available, and gravity is allowed to work at full depth. The compact region was not a weakness in the evidence. It was the strongest part of the case. A power source spread across a galaxy would have been easier to imagine and less revolutionary. A power source hidden inside the central light year of a galaxy was much harder, and for that reason much more revealing. The strongest thing the universe can create was beginning to take shape not as an enormous object filling space, but as an engine whose influence becomes enormous precisely because its power is focused so tightly near the centre. The link between quasars and galaxy centres did not arrive as a single neat answer. It gathered slowly from objects that looked different enough to seem unrelated. Some sources were loud in radio waves, with long structures reaching beyond the visible edge of their galaxies. Some were dominated by bright compact nuclei, as if the central light had swallowed the softer glow of every star around it. Some produced intense X-rays. Some appeared almost quiet in radio, but still carried unusual spectral lines and violent motion in their cores. At first, these differences encouraged separate names and separate categories, because astronomy often begins by sorting appearances before the underlying cause is clear. A quasar seemed like a star-like point at great distance. A radio galaxy seemed like a galaxy with enormous lobes of radio emission. A Seyfert galaxy seemed like a nearby spiral with a restless, brilliant centre. A blazar seemed stranger still, changing rapidly and shining with harsh intensity, as though its central engine had been aimed almost directly along the line of sight. The surface taxonomy was confusing, but the repeated pattern lay in the middle, again and again. The abnormal power came from the nucleus, from the innermost region where the galaxy's ordinary shape no longer seemed to be in command. This was the beginning of a broader idea: active galactic nuclei, a name less poetic than quasar, but more revealing. The activity was not spread evenly across the galaxy. It was concentrated at the core. That realization changed the scale of the problem. A galaxy can contain hundreds of billions of stars, immense clouds of gas, spiral arms, dust lanes, and a halo of dark matter reaching far beyond the visible disk. Yet in these systems, the defining power came from the centre, from a region so small compared with the galaxy that it should have been almost negligible by size alone. The nucleus had become more than a location. It had become an engine room. The most important clue was that different active galaxies could be arranged into a family if perspective and fuel were allowed to matter. A radio galaxy might display long jets and broad lobes because its outflows were seen from the side, spreading into surrounding space. A quasar might reveal the hot central accretion flow more directly, overwhelming the host galaxy with concentrated light. A blazar might be the same kind of system viewed nearly down the axis of a jet, so that radiation from fast-moving particles was focused toward the observer and made unusually bright and variable. This did not mean every active galaxy was identical in every detail. Their black holes had different masses, their fuel supplies varied, their magnetic fields, surrounding dust, and host galaxies gave each one its own history. But the family resemblance became harder to ignore. The universe seemed to be showing one physical system through many windows. The same central arrangement could look different depending on angle, activity level, and the amount of material available to fall inward. The dusty structures around active nuclei made this especially important. Near the core of an active galaxy, gas and dust do not form a simple transparent sphere. Much of the material may gather into a thick, obscuring ring or torus around the central region. From some directions, this torus hides the hottest inner light, blocking a direct view of the accretion disk and forcing astronomers to infer the central engine from infrared radiation, scattered light, or the extended jets. From other directions, the line of sight passes more cleanly toward the nucleus, and the bright inner region appears exposed. The difference between hidden and revealed can make two related objects seem like separate species. This is not merely a problem of appearance. It is a reminder that cosmic strength can be concealed by geometry. An engine may be equally powerful, yet a cloud of dust, a viewing angle, or the alignment of a jet can decide what reaches Earth. The active nucleus, therefore, had to be understood not as one visible object, but as a layered environment. At the center sits the compact dark mass. Around it, a disk of hot accreting matter glows across ultraviolet, optical, and X-ray wavelengths. Farther out, faster gas produces broad spectral lines, because its motion near the central mass smears atomic signatures across a range of wavelengths. Beyond that, slower and more distant gas produces narrower lines. Around much of the whole structure lies dust that absorbs harsh radiation and re-emits energy in infrared light. In some cases, narrow jets emerge from the inner region, carrying particles away at nearly the speed of light. This architecture allowed astronomers to connect observations that had once seemed disconnected. Broad lines indicated rapid motion close to a heavy center. Narrow lines indicated energized gas farther away. Infrared glow suggested dust warmed by hidden radiation. Radio lobes suggested jets transporting energy into the galaxy's surroundings. None of these clues alone told the entire story, but together they pointed inward. Something compact and massive was organizing the light, the motion, and the outflows. The idea of a central supermassive black hole became increasingly difficult to avoid. Before black holes were widely accepted as astrophysical realities, this was an uncomfortable direction. A black hole sounded like an absence, and an absence seemed like a strange candidate for powering the brightest objects known. Yet the contradiction fades when the surrounding matter is included. The black hole does not shine from within. It creates the conditions under which other matter shines fiercely before disappearing or escaping. It provides the deep gravitational well. It defines the velocities close to the center. It allows a small region to convert falling matter into radiation far more efficiently than a star converts mass through fusion. In an active galactic nucleus, darkness and brightness are not opposites. They are joined parts of the same system. The darker and deeper the center, the more energetic the surrounding fall can become. Observations of active galaxies also showed that these engines were not rare freaks placed randomly through space. They appeared in many galactic forms and across a wide range of cosmic distances. The strongest, most luminous quasars were common in the earlier universe, while nearby active galaxies often seemed less extreme. This distribution gave the family an evolutionary meaning. Galaxy centers could turn on and off. They were not permanently fixed in one state. A quiet galaxy might contain the same basic central machinery without currently having enough fuel to glow as a quasar. A galaxy disturbed by a merger or fed by fresh gas could send material inward and ignite a phase of activity. The active nucleus became an episode in a galaxy's life rather than a completely separate identity. This idea softened one mystery while sharpening another. It explained why quasars belonged mostly to the distant past. When galaxies were closer, gas was more abundant and mergers were more frequent. But it also implied that nearly every large galaxy might carry a dormant version of the same engine. The difference between a calm nucleus and a quasar could be a matter of feeding. This gave the Milky Way a new role in the story. It was no longer simply the place from which distant quasars were observed. It became a possible example of the same system in a quiet state. The band of the Milky Way hides its center behind dust in visible light, but radio and infrared observations can reach into that crowded region, there, at the heart of the galaxy. Astronomers found strong evidence for a compact massive object. The Milky Way is not a quasar today. Its central engine is faint compared with the great beacons of the early universe. Yet the existence of a massive dark object in its core suggested that the quasar mechanism was not exotic in location, only in activity. The same kind of central structure might sit inside ordinary galaxies, waiting for conditions that allow it to feed. This connection between the remote and the local made quasars easier to place inside a coherent universe. They were not violations of galactic structure, they were an extreme phase of it. The galaxy supplies the fuel, the central black hole supplies the gravitational depth. The surrounding gas and dust determine how the engine appears. The jets and radiation carry the consequences outward. With this view, the strange zoo of active galaxies became less chaotic, the whiskers, tail. And shadow belonged to one animal seen from different directions and in different moods. Still, the unifying picture did not remove the need for a nearer demonstration. If black holes in galaxy centers were truly the hidden engines, then the closest large galaxy available for detailed study was the one surrounding Earth itself. Its core was dim, obscured, and crowded, but it offered a chance to watch stars move under the rule of an unseen mass, to measure gravity not from brightness but from orbit. The path from the distant quasar therefore turns inward, toward the quiet center of the Milky Way, where the strongest engines in the universe leave their most intimate clue, not a blaze, but a pattern of stars circling something that cannot be seen. Sagittarius, a star, is quiet only by comparison. At the center of the Milky Way, behind curtains of dust thick enough to hide ordinary starlight, a compact radio source marks the position of the galaxy's central mass. It does not flood the galaxy with quasar light. It does not launch the kind of enormous visible beacon that would make the Milky Way unmistakable from across the universe. Yet its stillness is misleading, because the object beneath that radio glow carries the same basic identity as the engines that power quasars. It is a supermassive black hole, weighing millions of times the mass of the Sun, resting inside the most crowded region of the galaxy. Its present faintness is not a sign of weakness. It is a sign of hunger without much food. The Milky Way's center is dense by the standards of ordinary space, filled with stars, gas, dust, magnetic fields, compact remnants, and old stellar debris. But it is not feeding the black hole at anything like the rate needed to awaken a quasar. The engine exists. The fuel flow is thin. That distinction makes Sagittarius, a star, one of the most important objects in the story, because it gives the distant quasar a local shadow. The strongest long-lived engines in the universe are not made only by placing a black hole inside a galaxy. They require a surrounding supply of matter, a pathway inward, and the conditions that allow falling gas to become a luminous disk. Without that supply, the black hole remains dominant in gravity but modest in light. This is the state of the Milky Way today, a galaxy with a sleeping central engine, not an absent one. The first hints of that engine did not come from visible astronomy. The center of the Milky Way lies in the direction of Sagittarius, where the bright band of the galaxy becomes richest and most obscured. Along that line of sight, interstellar dust absorbs and scatters visible light so effectively that the true core is hidden from ordinary optical view. Radio waves are less easily stopped by that dust, so radio astronomy became the method that could enter the concealed region. In those observations, Sagittarius A appeared as a complex source of radio emission, and within it lay an especially compact point. The small point became Sagittarius A star, a name that carries the history of detection more than the nature of the object itself. It is not a star. It is the sign of a place where stars move around something unseen. The crucial evidence came from watching those stars over time. In the crowded central region, individual stars near the radio source trace tight, fast orbits, curving around a dark focus. These are not gentle paths like the wide orbit of the Sun around the galaxy. They are steep gravitational loops, some bringing stars close enough to the central mass that their speeds climb to thousands of kilometers per second. The stars themselves remain visible in infrared light, which can pierce much of the obscuring dust. Their motion provides a clean kind of measurement. Gravity reveals the mass that light cannot show. By following the orbits, astronomers found that millions of solar masses had to be packed inside a region far smaller than any ordinary star cluster could remain stable. A cluster of faint stars, neutron stars, or small black holes would either shine, evaporate, collide, or spread out over time. The mass was too concentrated, too dark, and too persistent. The simplest remaining answer was a supermassive black hole. This is a quieter proof than a blaze in a distant quasar, but it is in some ways more intimate. It does not depend on the total luminosity of an unresolved point across billions of light years. It depends on geometry and motion inside the Milky Way itself. A star approaches the center, bends around it, and departs along a path that can be measured again and again. The invisible mass holds the orbit. The repeated motion becomes a diagram of gravity. For decades, this orbital evidence tightened the case until alternatives became increasingly artificial. Then the Event Horizon Telescope added a different kind of confirmation. In 2022, after combining observations from radio dishes spread across Earth, the collaboration released an image of Sagittarius, a star's immediate environment. The picture was not a photograph in the everyday sense. It was a reconstructed view made from delicate radio measurements, processed with great care to reveal structure at the edge of what terrestrial instruments can resolve. It showed a glowing ring around a dark central shadow, the same basic signature expected when hot plasma surrounds a black hole. The ring is not the surface of the black hole. The black hole has no surface that light can leave. The dark center is the shadow produced by the event horizon and by the bending of light in severely curved space-time. Around it, plasma moves at relativistic speeds, heated and stirred as it orbits near the point of no return. The image did not turn Sagittarius, a star, into a quasar. It showed why the quasar explanation had become physically credible. At the heart of a galaxy, a supermassive black hole can exist. Around it, matter can become hot enough to glow in radio light. Near it, space-time can bend light so strongly that the object appears as a shadow wrapped in a ring. This is the local version of the same architecture that, under heavier feeding, becomes far more luminous. The difference is scale of activity. Sagittarius. A star accretes only a small amount of matter compared with an active quasar. Much of the gas near it may be too hot, too turbulent, or too angular in its motion to fall efficiently. Some may be blown away before it reaches the inner disk. Some may orbit without descending quickly. The black hole waits inside a messy environment where fuel is present but not delivered in a sustained torrent. That is why the Milky Way's core flickers and mutters rather than roars. Its radiation is real, but weak when compared with the great active nuclei of the distant universe. From outside the local group, the Milky Way would not be classified as a quasar. Its center would look underfed, almost restrained. Yet the restraint itself is instructive. It shows that a black hole's mass alone does not determine its visible power. A supermassive black hole can be enormous and still dim if little matter reaches the region where gravitational energy can be released. The strongest thing the universe can create is therefore conditional. It is not the black hole in isolation, however immense. It is the black hole in the right state, fed by the right inflow, wrapped in a disk, threaded by magnetic fields, and allowed to convert descent into light. Sagittarius, a star, holds the first part of that recipe. The Milky Way's history may hold evidence that it once held more. Above and below the plane of the galaxy, large bubbles of high-energy emission suggest that the central region has not always been so quiet. In the relatively recent past by galactic standards, Sagittarius, a star, may have consumed a larger supply of gas or disrupted material, producing outflows that carried energy far into the halo. These structures are faint compared with the giant lobes of powerful radio galaxies, but they imply memory. A sleeping black hole can leave traces of an earlier awakening. The Milky Way is not a permanent sanctuary from the physics of active nuclei. It is a galaxy between stronger episodes. This matters because it links human cosmic address to the same processes observed in the remote universe. The quasar is not an alien principle belonging only to unreachable distances. It is an extreme state of a mechanism present at home. The central black hole of the Milky Way is calm now because its conditions are calm enough, not because its nature is gentle. If a dense cloud, a cluster of stars, or the disturbed gas from a future galactic encounter were driven inward, the quiet ring of emission could grow brighter, an accretion disk could strengthen, magnetic fields could become more ordered and more violent, radiation from the core could rise by orders of magnitude. The objects now known through star orbits and a radio shadow could begin to resemble, in miniature or perhaps in full, the engines first found as impossible lights in the distant sky. Sagittarius. A star therefore closes the gap between observation and mechanism. It supplies the nearby proof that galaxy centers can hide massive dark objects, and it reveals why darkness does not prevent power. The black hole is not bright because it shines, but because it can make falling matter shine. In the present Milky Way, that process is subdued, in quasars. It is amplified until the nucleus overwhelms the galaxy around it. The same gravitational idea holds both states together, from a quiet central shadow to a beacon visible across cosmic time. What changes is not the existence of the abyss, but the amount of matter arriving at its edge. Accretion begins as an ordinary word for an extraordinary surrender. A cloud of gas near a galactic center does not need to be destroyed all at once to become part of a quasar. It only has to lose enough freedom. In the wide spaces of a galaxy, gas can drift, orbit, cool, collide, and form stars. Near a supermassive black hole, the same material enters a deeper hierarchy. Its motion is no longer governed mainly by the gentle combined pull of the galaxy, but by one compact source of gravity at the center. The gas may begin far from the event horizon, spread thinly through the inner region, carrying angular momentum from its earlier life in the galaxy. It cannot simply fall straight inward, because most of it is already moving sideways. Instead, it gathers into a rotating flow, circling the black hole while slowly giving up energy and shifting closer to the center. The important point is not that matter falls, because matter falls everywhere in the universe. The important point is how much energy can be released when the fall occurs near an object this compact. A gas particle descending toward a supermassive black hole moves into a region where space-time itself is strongly curved, where stable orbits tighten, velocities rise, and the old separation between motion and heat begins to blur. Falling becomes fuel because the descent is not quiet. Each part of the gas carries gravitational potential energy, a stored possibility created by its position in the gravitational field. As the gas moves inward, that stored energy has to go somewhere. Some remains in orbital motion, some becomes turbulence, some becomes heat, some leaves as radiation. The light is produced mostly before the matter crosses the event horizon, while the gas is still outside, crowded into the disk and forced into contact with neighboring streams moving at different speeds. The event horizon is the final boundary. The luminous engine is the region of approach. This is why a black hole can be visually associated with brilliance without violating its own darkness. Nothing escapes from inside the horizon, yet enormous amounts of energy can escape from matter still outside it. The accretion disk becomes the visible consequence of a hidden depth. The disk forms because angular momentum cannot vanish on command. A cloud that begins with even a modest amount of rotation will spin faster as it contracts inward, much as any rotating body speeds up when its mass is drawn closer to the axis. The inward path therefore becomes a spiral rather than a plunge. Gas in the inner disk orbits faster than gas farther out. Adjacent rings shear past one another. Magnetic turbulence and internal stresses allow angular momentum to be transported outward, so that some material can move inward. This exchange is slow compared with a direct fall, but it is exactly what allows the engine to persist if all the gas crashed inward at once. The quasar would be more like a brief catastrophe. Instead, the disk meters the descent. It releases energy step by step, orbit by orbit, through a structure that can remain bright as long as the galaxy continues feeding it. In that gradual release lies one of the great efficiencies in nature. Fusion inside stars converts only a small fraction of matter's rest mass into usable energy. The sun shines because it has an immense supply of hydrogen and the patience of billions of years, not because each bit of fuel gives up most of its possible energy. Accretion onto a black hole can be far more efficient. Around a non-rotating black hole, a significant share of the incoming matter's rest mass energy can be radiated before the material disappears. Around a rapidly spinning black hole, the efficiency can be higher still, because the innermost stable orbits lie closer to the horizon, and the gravitational well can be tapped more deeply. This does not mean matter is being casually converted into pure light. It means the path inward allows a large fraction of the energy associated with motion and position to be extracted before the final crossing. The result is an engine that can outshine stars not by burning like a star, but by using gravity as a furnace. The disk's heat is not uniform. Farther out, the material may be cooler, denser, and partly shielded by dust. Closer in, temperatures climb until atoms are stripped apart, leaving plasma, a sea of charged particles rather than neutral gas. Radiation emerges across many wavelengths. Strong emission from the inner disk can appear in ultraviolet light. Hotter regions and energetic scattering processes can produce X-rays. Surrounding dust can absorb harsh radiation and re-emit it in infrared light. To instruments across the electromagnetic spectrum, an active galactic nucleus is therefore not one color of fire, it is a layered release of energy. Each wavelength carrying information about a different region of the inflow. The brightest optical point may be only the visible face of a more complex conversion taking place near the center, yet the same brightness that reveals the engine also limits it. Light carries momentum. When the accretion disk becomes sufficiently luminous, its radiation pushes outward against the incoming gas. This outward pressure can oppose gravity, especially where the material is ionized and able to interact strongly with photons. If the engine grows too bright for the rate at which gravity can hold the inflow, radiation begins to drive gas away. The system resists overfeeding. This balance is often described through the Eddington limit, a threshold where outward radiation pressure and inward gravitational pull reach a critical relation for ionized gas. It is not an absolute wall in every environment, because disks can be uneven, flows can be clumpy, and geometry can open channels where radiation escapes more easily than matter falls. But it remains one of the central constraints on quasar power. The engine can be strong because gravity is deep. It cannot be arbitrarily strong forever, because the light it creates pushes back on the fuel that sustains it. That self-limiting quality gives quasars part of their strange steadiness. They are violent systems, but not simple explosions. The disk can brighten, push material outward, thin its own fuel supply, and then settle into renewed accretion when gas cools or fresh material arrives. A galactic merger can drive gas inward. The disk can ignite. Radiation and outflows can heat the surroundings. The fuel can be partly cleared or stabilized. Later, another disturbance can begin the cycle again. What appears as a long-lived beacon may contain internal variation, pulses of feeding, and changes in structure, all governed by the constant negotiation between gravity and escaping energy. This negotiation is not a flaw in the engine. It is part of how the engine lasts. The most extreme quasar is not merely the one that devours most quickly. It is the one that can keep matter arriving while still allowing energy to escape. Inside this balance, the idea of strength becomes more refined. A black hole does not need to throw energy outward by itself. It needs to hold open a deep gravitational drop. The galaxy does not need to send all its matter into the center at once. It needs to disturb enough gas that some of it loses angular momentum and joins the disk. The disk does not need to remain perfectly smooth. It needs turbulence, because without internal stresses, material would orbit without descending. The radiation does not simply illuminate empty space. It records the work done by gravity on matter. Across millions of years, those withdrawals add up to one of the largest sustained outputs known in the universe. The quiet elegance of the mechanism can be easy to miss because the result is so severe. Gas that might once have formed stars is instead heated to plasma. Orbits that might have remained stable are dragged inward by friction and magnetic stress. Matter that once belonged to a galaxy becomes fuel for a nucleus bright enough to dominate that galaxy's light. Yet there is no new law of physics invented for the purpose. The process uses familiar principles under unfamiliar conditions. Conservation of angular momentum shapes the disk. Gravity supplies the energy gradient. Electromagnetic interactions allow charged matter to radiate and exchange momentum. Relativity defines the inner boundary and the depth of the well. The extremity comes from placing these principles beside a supermassive black hole, where small distances contain enormous gravitational meaning. Falling as fuel also explains why quasars are so compact compared with their influence. The main release does not require a region as wide as the galaxy. It requires matter to reach the central zone where orbital energy can be shared efficiently. A disk with a size small on galactic terms can still outshine the stars around it, because each unit of mass passing through the inner region gives up so much energy. This is the hidden arithmetic behind the impossible lights. Their power does not come from having the most fuel spread across the largest volume. It comes from sending fuel through the deepest available channel. Still, accretion alone does not fully explain the long reach of quasars. Light can radiate in all directions, heating what it encounters, but some quasars do more than shine. They launch narrow streams of particles that remain coherent over astonishing distances. For that, the falling gas must be joined by another part of the system, one that turns rotation, plasma, and magnetic fields into directed escape. Gravity lights the disk. But magnetism gives the engine a blade. Gravity lights the inner disk, but it cannot by itself explain the long, narrow structures that make some quasars look as though a galaxy has fired through its own skin. For that, the engine needs plasma and magnetic fields near the black hole. Ordinary gas has already lost much of its old form. Heat has stripped electrons from atoms, leaving charged particles that respond to electric and magnetic forces as naturally as dust responds to wind. The disk is not only rotating, it is conducting, turbulent, and threaded with loops and instabilities, each shaped by the same differential motion that makes the inner material orbit faster than the outer material. Magnetic field lines are not material threads, but in a plasma they can behave as if they are partly tied to the moving gas. As the disk turns, those fields are dragged, twisted, stretched, and wound tighter. The result is not a passive glow around a dark center. It is an electromagnetic machine built inside a gravitational one. The black hole supplies the depth, the disk supplies the motion. The The plasma gives magnetism something to grip. At first, the field may be weak, seeded by the galaxy, by earlier stars, or by the turbulent gas itself. Weakness does not remain weakness for long in a rotating disk. Small magnetic disturbances are amplified by motion, and the disk becomes unstable in ways that help it feed the black hole. Material cannot move inward efficiently unless angular momentum is carried outward. Magnetic stresses provide that exchange. They allow one layer of gas to pull against another, passing rotation outward while permitting some matter to descend. The same process that helps accretion continue also strengthens the magnetic structure around the center. The disk therefore prepares its own escape routes even as most of its matter moves toward capture. Near the innermost stable orbits, the contrast becomes severe. Gas inside that boundary can no longer remain in a secure circular path. Much of it plunges toward the event horizon, adding its mass to the black hole and removing itself from view. But not every charged particle follows the same fate. Some are guided along magnetic fields that rise above and below the disk. In these polar regions, the density can be lower, the field geometry cleaner, and the path away from the center less obstructed. The disk is flattened by rotation, but the magnetic field can open vertically, creating channels through which energy escapes. This is where a quasar begins to look less like a lamp and more like a lance. The jet is not simply matter thrown away by an explosion, it is a collimated outflow, focused into a narrow stream by magnetic structure and powered by the energy stored in rotation, accretion, and in some models the spin of the black hole itself. The idea that a spinning black hole can help launch a jet is one of the most striking consequences of relativity near the horizon. A rotating black hole drags space-time around with it, forcing the nearby region into motion. Outside the event horizon lies a zone where remaining still with respect to the distant universe becomes impossible. This region is called the ergosphere, a domain of compelled rotation rather than a solid surface. Magnetic fields that thread this region can, in principle, tap some of the black hole's rotational energy. The Blandford-Znajek process describes one way this may happen. In that picture, magnetic fields anchored in the surrounding plasma penetrate the spinning environment near the black hole. The rotation twists the fields, sets up powerful electromagnetic flows, and carries energy outward along the poles. The black hole remains dark at its boundary, but its spin can be part of the circuit that feeds the jet. This does not mean the process is simple or finally settled in every detail. Jets are difficult because they involve gravity, relativity, turbulent plasma, radiation, and magnetic fields all at once. Their launching regions are extremely small on galactic scales and often too distant to observe directly. Yet the broad pattern is clear enough to be compelling. Where black holes feed strongly and magnetic fields organize efficiently, narrow outflows can form. These outflows carry charged particles at relativistic speeds, often so close to the speed of light that time, brightness, and direction are altered by their motion. If a jet points nearly toward Earth, its radiation can be intensified by relativistic beaming, making the source appear unusually bright. This is why blazars seem so extreme. They are active engines whose jets are aimed along the line of sight, allowing motion itself to amplify the signal. Seen from the side, the same kind of outflow may reveal a different architecture. A narrow jet emerges from the nucleus, travels through the host galaxy, and strikes the thinner gas beyond it. Over time it inflates vast lobes of radio emission. The radio glow comes from charged particles spiraling around magnetic fields, producing synchrotron radiation. In maps of powerful radio galaxies, the scale can be startling. A central black hole, smaller than the solar system in its horizon scale, can drive jets that extend for hundreds of thousands or even millions of light years. The mismatch is not a visual trick. It is the consequence of sustained energy transport. The engine is compact, but it keeps launching particles in electromagnetic power along preferred directions, allowing influence to accumulate far from the point of origin. These jets are among the clearest reasons quasars deserve to be called engines rather than lights. A light source radiates. A jet performs work. It pushes into surrounding gas. It excavates cavities. It heats the medium between stars and, in the richest environments, the hot gas-filling galaxy clusters. When the jet finally slows, its energy does not vanish. It is deposited into bubbles and shocks, raising temperatures and changing how gas cools. This feedback can prevent gas from collapsing too quickly into new stars, linking the innermost region of a black hole to the life of an entire galaxy. The magnetic blade that begins near the horizon can therefore become a sculptor, at scales the black hole itself will never physically occupy. The jet also carries a kind of memory. It records the direction of the black hole's spin, the structure of the accretion disk, and the history of feeding episodes. Some jets appear straight across enormous distances, implying a stable engine axis over long spans of time. Others bend, knot, or flare, suggesting encounters with surrounding gas or shifts in the central system. Bright knots along a jet may mark shocks where faster material catches slower material or where the outflow encounters resistance. These details turn jets into fossil tracks of activity. They show not just that energy escaped, but how it travelled and where it struck. The most powerful examples transform their environments into enormous radio structures, with twin lobes extending on opposite sides of a galaxy like paired reservoirs of spent force. That symmetry is a clue to the central origin. The engine does not throw energy randomly in every direction. Rotation gives it an axis, magnetism gives it confinement, plasma gives it carriers. The result is two opposite channels, one approaching and one receding. Though perspective and relativistic effects may make one side look brighter than the other, still, the jet is only one face of the quasar. Around it, the accretion disk continues to radiate. Beyond it, dust absorbs and reprocesses light. Farther out, clouds of gas glow under ultraviolet and X-ray radiation. The system is not a single beam, but a layered engine with both broad illumination and narrow escape. The jet is what gives certain quasars their reach, but it depends on the same feeding that powers the disk, without matter falling inward. The magnetic structure weakens. Without plasma, the fields lose their carriers. Without rotation, the geometry cannot remain focused. The strongest engine is therefore a coordination of conditions, not a solitary miracle. This coordination also explains why not every active galaxy produces a spectacular jet. Some black holes may lack the right spin, the right magnetic flux, the right disk state, or the right supply of infalling gas. Some nuclei shine brightly without becoming radio loud. The family of active galaxies keeps its variety because the central recipe has adjustable parts. Feeding rate, black hole mass, spin, magnetic field strength, surrounding dust, and viewing angle all change the appearance. But when the recipe reaches its most powerful form, the consequence is unmistakable. A feeding black hole can become a magnetic accelerator whose particles cross galactic distances and leave radio scars across the intergalactic medium. The strange radio points that began the quasar story were therefore not incidental signals. They were one of the outer signs of this hidden electromagnetic structure. Early astronomers heard the distant jets before they understood the engines that launched them. The radio waves were the echo of charged particles spiraling through fields that had been twisted near supermassive black holes. Once that connection is made, the old pinpricks in the radio sky acquire a physical depth. They are systems that draw matter inward and send energy outward, where gravity and magnetism divide the fate of falling material into disappearance below the horizon and escape across the galaxy. The jet shows that a quasar's strength is not confined to the place where it is born. It becomes strongest when the central engine finds a way to project itself outward, turning a dark compact mass into a structure that can reach through the galaxy and into the thin spaces beyond. The power of a quasar does not end when light leaves the accretion disk or when a jet escapes the central region. That escaping energy enters a galaxy that is already trying to become something else. Gas cools, clouds collapse, stars form, massive stars die, and their debris returns to the surrounding medium. Left alone with enough cold material, a galaxy can turn gas into stars rapidly, sometimes too rapidly for its own long future. Quasar feedback is the name for the interruption. It is the process by which the central engine pushes back on the galaxy that feeds it, heating gas, stirring the inner regions, driving winds outward, and sometimes preventing new stars from forming as efficiently as they otherwise would. A black hole may occupy almost no physical volume compared with its host galaxy, yet, when it feeds strongly, it can regulate the fate of gas across distances that make the event horizon seem absurdly small. The nucleus becomes a thermostat with a gravitational abyss at its center. This connection first seems unlikely because the scales are so different. A galaxy is an extended system of stars, dust, gas, and dark matter. Its visible disk may stretch for tens or hundreds of thousands of light years, and its halo reaches farther still. The active region around the black hole is tiny by comparison. Even the broad environment of the accretion flow is only a central knot inside the galaxy. Yet energy does not need to fill space evenly to alter it. A jet can carve a channel through gas. Radiation can ionize and heat clouds. Winds from the disk can push material outward. Cosmic rays can add pressure where ordinary heat is not the whole story. Over time, these effects accumulate. The engine does not have to touch every cloud directly. It only has to change the conditions under which clouds cool, fragment, and collapse. Star formation is sensitive to temperature, density, turbulence, and pressure. Quasar activity can disturb all of them. Cold gas is the immediate raw material of stars. When a cloud becomes dense and cool enough, gravity can overcome internal pressure and pull the material inward. The process is not simple, because magnetic fields, rotation, turbulence, and radiation all interfere. But cooling remains essential. Hot gas resists collapse. It expands more easily, moves faster, and can remain suspended in a diffuse state rather than condensing into stellar nurseries. A quasar supplies heat in several ways. Its radiation pours through the inner galaxy, ionizing atoms and raising gas temperatures. Its winds slam into surrounding material, producing shocks. Its jets inflate cavities in hot atmospheres around massive galaxies and clusters, stirring the medium and preventing it from cooling quickly. The result can be a break on star formation, not a total stop in every case, and not a gentle adjustment, but a change in the rate at which a galaxy consumes its fuel. This is where destruction begins to look like regulation. If a young or merging galaxy gathers a large supply of gas, that gas can trigger a powerful starburst. For a time, star formation rises sharply. New massive stars appear in great numbers, burn quickly, and explode. But if the burst runs unchecked, the galaxy may exhaust or expel much of its cold gas too soon. It may become bright for a short chapter, and then fade into relative quiet, with little material left to build later generations of stars. Quasar feedback offers a counterweight. As gas flows inward and feeds the central black hole, the nucleus brightens. As the nucleus brightens, it heats and disturbs the same broader reservoir from which stars would have formed. The feeding black hole responds to the growth of the galaxy by limiting the conditions that made the feeding possible. This is not intention, it is coupling. The galaxy and its black hole become linked through shared gas. One of the strongest clues to this linkage comes from the relationship between supermassive black holes and the galaxies that host them. Black hole mass is not random with respect to the surrounding galaxy. It correlates with properties of the central bulge, including the speeds of stars moving within that region. This does not mean the black hole controls every detail of the galaxy, or that every galaxy follows one perfect rule. But the pattern is too suggestive to ignore. The central black hole and the host galaxy appear to grow together, each shaped by the inflow, heating, and removal of gas, without feedback. It is difficult to explain why black holes do not grow too large whenever fuel is abundant, or why massive galaxies do not cool their surrounding gas into far more stars than are observed. The quasar becomes part of the accounting. It spends energy in a way that changes the future supply. In clusters of galaxies, the evidence can become almost architectural. The space between cluster galaxies is filled with extremely hot, thin gas, visible in X-ray light. In many clusters, the central galaxy contains an active black hole, whose jets push into this gas and excavate vast cavities. These cavities are bubbles inflated by relativistic particles and magnetic fields, regions where the jet has displaced the hot medium around it. Around them, shocks and ripples can carry energy outward. The effect is subtle compared with a single explosion, but persistent enough to offset cooling. Without such heating, gas in cluster centers should often cool, condense, and form stars at rates higher than what astronomers see. The active nucleus solves part of that discrepancy by reheating the environment. A black hole smaller than a star system can help govern the thermal balance of a cluster core. This does not make quasar feedback simple. It can be positive as well as negative. A jet ploughing through gas may compress certain clouds and trigger star formation along its path. A wind may clear dust from a region and change how radiation travels. A merger may feed both a starburst and an active nucleus at the same time, making cause and effect difficult to untangle. In some galaxies, quasar activity may end a burst by driving gas away. In others, it may merely delay cooling. In still others, it may redistribute gas rather than remove it. The same engine can have different consequences depending on the density of the surroundings, the angle of the jet, the depth of the galaxy's gravitational well, and the duration of the active phase. Feedback is therefore not a single outcome. It is a family of interactions between an engine and the material around it. The most important feature is self-regulation. When little gas reaches the black hole, the nucleus stays faint and its influence weakens. When a great deal of gas reaches the center, the accretion disk brightens. Winds strengthen and jets may intensify. That increased output can heat or expel gas, reducing the supply that continues inward. The system can throttle itself. It is not stable in the sense of stillness. It is stable in the deeper sense of a cycle that resists extremes. This may be why many galaxies live long, productive lives instead of converting all available gas into stars in one early blaze. The central black hole, often imagined only as a devourer, becomes a participant in preserving the galaxy's slow evolution. It limits excess by becoming bright when excess feeds it. For the Milky Way, this idea gives the quiet center a deeper past. Sagittarius. A star is not acting as a quasar now, but structures above and below the galactic plane suggest earlier activity. Giant gamma-ray bubbles extending from the central region appear to record a time when the nucleus or the surrounding star-forming activity injected energy into the halo. The Milky Way has not always been as calm as it looks from the position of the Sun. It carries traces of central disturbance. smaller than the grandest radio galaxies, but still large enough to remind that a sleeping black hole is not inert. If earlier feeding episodes helped heat gas or regulate star formation, then the central black hole may have shaped the conditions under which later stars, including the Sun, formed in a more measured galactic environment. The strength of a quasar is therefore not only the brilliance seen from far away, it is the ability to couple a tiny central region to the life of a galaxy. Radiation leaves the disk, winds leave the inner flow, jets leave the nucleus. Each carries energy from the black hole's feeding zone into matter that may never come near the event horizon. This outward reach changes the meaning of the engine. A quasar is not merely consuming its host, it is communicating with it through heat, motion, pressure, and delay. It can starve itself by disturbing its own fuel supply. It can quiet a galaxy by warming gas that would otherwise collapse. It can inflate bubbles larger than galaxies and alter the medium through which future galaxies move. In this sense, the strongest thing the universe can create is not just an object with power, but a system whose power returns to shape its source. The black hole feeds on the galaxy, and the galaxy is changed by the feeding. The loop is imperfect, variable, and still not fully understood. But it gives quasars a role far larger than their light. They are not only beacons of the early universe, they are one of the ways the universe learned to keep its galaxies from burning through their futures too quickly. The early universe should not have had much time to build monsters. After the first light elements formed and the cosmic fire cooled enough for atoms to hold together, there were no stars yet, no mature galaxies, no heavy elements spread through space. Matter was present, but structure had to grow from small beginnings. Slight differences in density pulled more matter toward themselves. Gas gathered inside dark matter halos. The first stars ignited in a universe chemically simpler than the modern one. The first galaxies assembled from smaller clumps. In that young setting, quasars appear almost too soon. Their light reaches the present from epochs when the cosmos was only a small fraction of its current age, and yet the engines implied by that light are not modest. They require black holes already weighing millions or billions of solar masses, surrounded by enough gas to shine across distances so large that the signal arrives as a relic from near the dawn of galaxies. The difficulty is not that black holes exist early. Massive stars can live quickly and die quickly, and their remnants can form black holes after only a short cosmic interval. The difficulty is making the remnants grow into supermassive engines before the universe has had much time to provide the usual steps. A stellar remnant begins with limited mass. Even if the first stars were larger than many stars today, their deaths do not automatically produce the kind of central black hole needed to power the brightest early quasars. Growth has to follow, matter must be accreted, other black holes may have to merge, gas must reach the centre without being blown away. The surrounding galaxy must assemble rapidly enough to supply fuel. Each requirement can happen in principle, but the timing becomes severe when all of them must happen together. This is the early universe problem in its most direct form. The observed quasars seem to require black holes that grew faster than the simplest stories allow. The growth by accretion is powerful, but it is not free of limits. A black hole that feeds from a disk can convert gravitational energy into radiation with great efficiency. That efficiency makes quasars bright, but it also creates resistance. The radiation pushes outward on the same ionized gas that is trying to fall inward. If the inflow becomes too intense, the light generated by the disk can drive fuel away, reducing the supply before it crosses the horizon. The Eddington limit describes the balance between the inward pull of gravity and the outward pressure of radiation for such gas. It is not an unbreakable law in every messy astrophysical situation, because real accretion flows can be clumpy, tilted, obscured, or channeled through thick disks. Still, It is a serious constraint. A black hole cannot simply swallow unlimited matter while shining at quasar power without confronting the pressure created by its own brilliance. The engine's strength becomes part of the obstacle to its growth. Mergers offer another route, but they also carry difficulties. In the crowded early universe, small galaxies merged often, and their black holes could be brought into the same larger system. At large distances from each other, friction with stars and gas can help them sink toward the center. As they become a tighter pair, their orbit loses energy. Eventually, when they're close enough, gravitational waves can drain the final orbital energy and cause the black holes to coalesce. But there is a troublesome middle stage. Once two black holes become separated by only a few light years or less, the surrounding matter may not always remain efficient at removing energy from the pair. Gravitational waves may still be too weak until the orbit becomes tighter. This difficulty is often called the final parsec problem, a name for the gap between bringing black holes together and making them finish the merger. The universe clearly does finish some mergers, because gravitational waves from black hole collisions have been detected, and many galaxy centers contain only one dominant supermassive black hole despite long merger histories. But knowing that the problem is solved somewhere in nature does not automatically show how it was solved quickly enough, often enough, and early enough to build the first brilliant quasars. The missing middle weights the question with uncertainty. Another clue comes from what is difficult to find. If supermassive black holes grow gradually from smaller stellar remnants, then intermediate mass black holes should be an important bridge. These objects would weigh more than ordinary stellar black holes, but less than the giants and galactic cores. They should represent growth in progress between massive stellar deaths and quasar engines. Candidates exist, and some are persuasive, but the population is not as clear or abundant as a simple growth picture might suggest. The absence of an obvious bridge does not prove the bridge is missing. Intermediate black holes may be hard to detect because they are faint, wandering, hidden in dense star clusters, or active only rarely. Yet the uncertainty matters. A clean sequence from small remnants to intermediate objects to supermassive black holes would make the story easier. Instead, the evidence remains uneven, with giant black holes appearing clearly in galaxy centers, while many of the expected transitional cases stay elusive. The early quasars sharpen that unease because they sit at the end of the ladder before the lower rungs have been securely mapped. Their host galaxies also raise pressure on the timeline. A quasar is not only a black hole, it is a black hole with an organized feeding environment. Gas has to be present in large quantities. It has to lose angular momentum and move inward. The central region has to form an accretion flow capable of radiating strongly. If jets are present, magnetic fields must be arranged in a way that allows energy to escape along an axis. All of this must happen inside young galaxies that are still assembling themselves from smaller structures. The early universe was denser, and that helps. Galaxies were closer together. Gas supplies were richer. Mergers were more frequent. Gravity had less empty space to cross before encounters happened. These conditions make rapid feeding more plausible than it would be today. But they also make the environment chaotic. Gas can be stirred, heated, expelled by stellar explosions, or disrupted by the very quasar it feeds. Building a stable enough engine inside a rapidly forming galaxy is not just a matter of having more material available. The material must arrive in the right way. Observations keep making the problem more precise. As telescopes detect quasars from earlier times and measure the masses of their central black holes, the available growth window becomes narrower. Some early quasars appear so luminous that the black holes powering them must already be enormous. Their existence does not break cosmology, but it pressures the models of how structure formed. It asks whether the first stars were different enough to leave heavier seeds. whether gas clouds could collapse directly into larger black holes, whether early accretion could exceed ordinary limits for long periods, or whether some more exotic route supplied the initial mass. Those possibilities belong to the next step in the story, but the need for them begins here, with the simple mismatch between time available and mass observed. The universe seems to have produced mature central engines while the cosmic architecture around them was still young. There is a deeper tension hidden inside the word mature. A quasar does not look embryonic just because it appears early. It is already performing the full work of an active galactic nucleus. It shines, heats, pushes, and perhaps launches jets. It is already tied to the growth of its host galaxy. It is already part of feedback. This means the black hole and the galaxy have entered their mutual relationship quickly. The central engine is not waiting for the galaxy to become settled. It is active during the era of assembly itself. In one sense, this may help explain the rapid growth of both. The same violent conditions that make early galaxies unstable may also drive gas inward efficiently. Disturbance becomes fuel, but in another sense, it complicates the picture, because the quasar's own radiation can interfere with the feeding that made it possible. The young engine must grow while resisting the consequences of its growth. That paradox gives early quasars their special weight. They are not merely distant versions of nearby active galaxies. They are evidence that the universe found a shortcut, an acceleration, or a more efficient pathway during its first major era of structure formation. The known laws still guide the discussion. Gravity gathers matter, gas cools and collapses, stars form and die, black holes accrete and merge, radiation pushes back, magnetic fields shape plasma. Nothing in the observation requires abandoning physics, but the order, speed, and efficiency of the steps remain unsettled. The strongest things the universe creates may not require impossible laws, only unusually favourable conditions operating at the edge of known limits. The early quasars sit exactly on that edge. Their light says that the engines were there, their redshifts say that they were there early, their luminosities say that the engines were already massive and feeding. What remains unclear is how the first seeds became large enough fast enough to make such brilliance possible. The question narrows toward the beginning, not how a quasar shines once the black hole is immense, but how the universe made the first immense black holes at all. The search for the first quasar seeds begins before the quasar can shine, once a supermassive black hole is already in place. The broad outline of the engine is understandable, gas falls inward, a disk forms, radiation escapes, magnetic fields may launch jets, and feedback begins to shape the host galaxy. The harder question lies farther back, in the stage before the engine has enough mass to become obvious. A black hole must begin somewhere. It may begin as the remnant of a massive star, or as the direct collapse of a large cloud, or perhaps from stranger conditions in the earliest moments of the universe. Each possibility changes the opening move of the story. If the seed is small, growth must be very fast. If the seed is large, the universe must make it without first building a normal star. If the seed is primordial, then black holes are not merely the products of stars and galaxies, but relics of the young cosmos itself. None of these routes is settled as the single answer. The early quasars may even require more than one pathway. The first and most conservative route begins with the first stars. In the modern universe, star formation is shaped by elements heavier than hydrogen and helium. These heavier elements help gas radiate away heat, fragment into smaller clumps, and form stars across a range of masses. The first star-forming clouds did not have that chemical richness. They were made mostly of hydrogen and helium, and their cooling pathways were more limited. Under such conditions, the first stars may have grown much larger than typical stars today. A very massive first star could live briefly, burn intensely, and die in a collapse that leaves a black hole heavier than the remnants of most modern stellar deaths. This kind of seed has the advantage of relying on processes already connected to known astrophysics gas collapses. Stars form, massive stars die, and black holes remain. But even if the first stars were enormous, their remnants may still have struggled to reach quasar scale quickly enough. A seed of tens, hundreds, or perhaps even a few thousand solar masses still has to cross a vast gulf before it becomes a billion solar mass engine. The clock in the early universe does not pause while that happens. Radiation pressure, supernova feedback, and the shallow gravity of young galaxies can interrupt the inflow. The first route is plausible, but it may not be generous enough for the most extreme early quasars. A heavier starting point comes from direct collapse. In this scenario, a large cloud of pristine gas avoids fragmenting into many ordinary stars. Instead of breaking apart, it loses support and collapses more coherently toward the center, forming a massive black hole seed without passing through the life of a normal star. This route is attractive because it begins with much more mass. A direct collapse seed could be large enough that later accretion has less work to do. But the conditions are demanding. The gas must remain hot enough to resist fragmentation, yet still collapse overall. Molecular hydrogen, which can help gas cool, may need to be suppressed by radiation from nearby young stars. Angular momentum must be transported away so that the material does not simply settle into a broad rotating structure. The cloud must avoid being disrupted before the collapse reaches the point of no return. Direct collapse is therefore not an everyday event in early galaxies. It is a special pathway, perhaps rare, but rare may be enough. The universe does not need every young galaxy to make a giant seed. It only needs some of them to do so, and those would naturally become ancestors of the brightest early quasars. Another route asks whether dense clusters of early stars could build a black hole by repeated collisions. In a young, compact stellar system, massive stars may sink toward the center through gravitational interactions. If the cluster is dense enough, collisions and mergers among stars can create one very massive object before the first supernovae disperse the gas. That object could then collapse into a black hole larger than an ordinary stellar remnant. This pathway lies between the first star route and direct collapse. It still uses stars, but it uses the crowded environment of a young cluster to assemble a larger central mass quickly. Its difficulty is timing. Massive stars live short lives, so the runaway growth has to occur before explosions and radiation reshape the cluster. The cluster must be dense enough, the gas must remain bound long enough, and the final collapse must leave a black hole rather than destroy too much mass, like direct collapse. It may not happen often, but the early universe was full of compact, gas-rich environments where rare channels could matter. A more speculative possibility reaches beyond ordinary matter and asks whether dark matter could help. Dark matter dominates the mass of galaxies. Yet it does not shine, absorb light, or interact strongly with ordinary atoms. In the simplest pictures, it gathers into broad halos and provides the gravitational scaffolding inside which gas forms galaxies. Because it does not easily cool or radiate, it does not normally collapse into small dense objects in the way ordinary gas can. But if dark matter has properties beyond the simplest assumptions, if it can interact with itself even weakly, or lose energy through hidden processes, then it might form denser central structures in the young universe. Under special conditions, such concentrations could influence black hole formation, or perhaps collapse into black holes directly. This remains uncertain and model dependent. Its value is not that it offers a confirmed solution, but that it shows how early quasars can test the nature of matter itself. Stranger still are primordial black holes, hypothetical objects formed not from stars, but from extreme density fluctuations in the very early universe. In the first moments after the Big Bang, before stars or galaxies existed, conditions were hot, dense, and rapidly changing. If some regions were dense enough, they might have collapsed directly into black holes. Depending on their mass and abundance, such primordial black holes could later act as seeds for supermassive growth. This possibility is tightly constrained by many observations. Too many primordial black holes of certain masses would affect cosmic background light, gravitational lensing, galaxy formation, or the motions of stars in ways that are not observed. Large regions of possibility have been narrowed or ruled out. Yet the concept has not vanished completely, because some windows remain uncertain, and because even a small number of primordial seeds in the right environments could have large consequences. A primordial seed would offer the most radical shortcut. It would mean that some black holes were older than the first stars, waiting inside the dark matter scaffolding before galaxies became luminous. Each seed pathway has its own cost. Stellar remnants are natural but often too small. Direct collapse seeds are large but require finely arranged conditions. Dense stellar clusters can build mass quickly but must outrun their own feedback. Dark matter-assisted routes depend on uncertain physics. Primordial black holes reach deepest into speculation and are constrained by what the universe does not show. The strength of the problem is that none of these answers can be accepted merely because it is elegant. The early quasars are real observational anchors, and the proposed seeds must eventually match their abundance, masses, host galaxies, and timing. A model that makes large seeds too easily may overproduce quasars. A model that makes them too rarely may fail to explain what telescopes find. A model that grows them too gently may miss the highest redshift engines. The problem is a balance between possibility and population. The universe had to make not just one remarkable object, but enough of them to match the sky. Observations are beginning to press on this balance. The James Webb Space Telescope has pushed deeper into the era of early galaxy formation, finding young galaxies and active black hole candidates that sharpen the question of how quickly massive structures appeared. Some detections remain difficult to interpret, because estimating black hole mass and separating active nuclei from stellar light at such distances is challenging. Still, the early universe appears to have been efficient at building luminous structures. Some masses may be revised, but the broader pressure will not disappear easily. The seeds of darkness are therefore not only an origin story for quasars, they are a test of how structure begins. They ask how gas behaved before heavy elements were common, how early radiation shaped collapse, how black holes move through young galaxies, how often mergers finished, and whether known physics under rare conditions can do what ordinary conditions cannot. The strongest engines in the universe may owe their existence to moments when the young cosmos found narrow paths through many obstacles, a little more cooling, and the gas fragments into stars, a little more feedback, and the fuel is blown away. Too little initial mass, and the black hole cannot grow fast enough. Too much abundance, and the universe would look different from what is observed. Somewhere among these constraints, the first quasar seeds formed. They were not yet the brightest beacons in existence. They may have been hidden, faint, and surrounded by chaotic young gas. But once they existed, gravity had a centre to deepen, matter had a place to fall, and the future quasar had begun its slow conversion from darkness into one of the most powerful lights the universe would ever make. The word strongest usually points toward resistance. It suggests something that cannot be broken, a material that holds its shape under pressure, a body that survives impact, heat, and strain. By that definition, the universe offers astonishing candidates. The crust of a neutron star may contain matter squeezed into forms far stronger than any ordinary solid. Atomic nuclei there are packed into strange shapes by gravity and nuclear forces. creating deep stellar material sometimes described as nuclear pasta. A magnetar can hold magnetic fields so intense that atoms themselves are distorted by their presence. A black hole can make a boundary from which no path outward remains. Each of these objects expresses strength in a different language: rigidity, density, magnetism, capture. Yet quasars force the word to widen. They are not strongest because they are hardest to dent, or because their surface survives the greatest stress. They may not have a surface at all in the way a planet or star does. Their strength lies in duration, conversion, and reach. A quasar takes a compact central engine and couples it to enormous distances. It draws matter inward through gravity and sends energy outward through radiation, winds, and jets. It is strong not only because it is bright, but because it keeps changing the environment that tries to feed it. This is a different category of cosmic power. An explosion can exceed almost anything for a moment. In the brief violence of a supernova or a gamma-ray burst, energy pours out with stunning intensity, and for a short time the event may rival or surpass entire galaxies. But the universe does not measure consequence only by peak brightness. A brief flash can mark an ending. A quasar marks a working state. It may shine for millions of years, sustained by the slow delivery of gas into the central regions of a galaxy. Over such spans, even a power that varies, dims, and brightens can deposit more total energy into its surroundings than a single outburst. The engine endures long enough for feedback to matter. It heats gas that would otherwise cool. It sends particles into regions far beyond the visible nucleus. It can stir the atmosphere of a galaxy cluster, leaving cavities, shocks, and radio lobes as records of repeated work. Its strength is cumulative. It acts not as a hammer blow alone, but as pressure maintained across cosmic time. That endurance changes how size should be understood. The event horizon of a supermassive black hole may be enormous compared with human scales, but it is still tiny compared with the galaxy around it. The luminous accretion region is also small on galactic terms, yet from that concentrated centre, influence spreads across tens of thousands, hundreds of thousands, or even millions of light years. The mismatch is the point. Quasar power is focused at birth and expansive in consequence. A central region smaller than the galaxy by a staggering margin can dominate the light of the entire system. A jet launched from near the black hole can remain organized long enough to pierce the galaxy and inflate structures outside it. Radiation from the disk can flood surrounding clouds. Winds can carry momentum into the interstellar medium. The strongest thing is not necessarily the widest object. It may be the object whose energy crosses the greatest difference between origin and effect. Quasars are also strong because they are efficient. Stars are majestic, but their fusion turns only a small fraction of available mass energy into light over long lifetimes. Black hole accretion can extract energy from matter falling into a much deeper gravitational field. The gas only needs to approach a region where orbital motion, heat, magnetic stress, and relativistic gravity force it to give up energy before it vanishes or escapes. A small amount of matter can produce extraordinary luminosity when fed through such a well. This efficiency makes a quasar feel almost unnatural at first. It appears to get too much from too little. But that is only because ordinary intuition is trained by weak gravity. Near a supermassive black hole, falling is no longer a quiet motion. It is a conversion process with consequences visible across the observable universe. Still, efficiency alone would not make quasars the strongest sustained engines. The energy must also leave. If all matter simply crossed the horizon without radiating, the black hole would grow in darkness. If all radiation were trapped, the surrounding galaxy would not feel the same outward force. The quasar becomes powerful because the environment outside the horizon allows energy to be released and transported. The accretion disk shines before the final crossing. Magnetic fields organize charged particles. Jets provide narrow escape routes. Dust absorbs harsh light and sends it back out in infrared wavelengths. Gas clouds reprocess radiation into spectral lines. Every layer translates the central fall into an observable effect. The black hole is the anchor, but the quasar is the system of translation around it. It turns hidden gravity into public energy. This is why a quasar can be both destructive and constructive in the broad story of galaxies. It destroys in the immediate sense. Gas is heated. Stars can be torn apart if they stray too close. Matter loses its old structure and becomes plasma, radiation, or fuel. Jets can batter their way through surrounding material. But at larger scale, the same activity can prevent a galaxy from exhausting its gas too quickly. By slowing cooling, stirring reservoirs, and limiting runaway star formation, quasar feedback may help a galaxy keep forming stars over longer periods, rather than spending its fuel in one uncontrolled burst. The engine consumes, but it also regulates consumption. That paradox makes it stronger than a simple destroyer. A simple destroyer only removes. A quasar changes the terms under which growth continues. It is part furnace, part brake, part beacon, and part sculptor. The strongest thing the universe creates may therefore be a relationship rather than a single object. The supermassive black hole alone is dark. The gas alone is ordinary galactic material. The magnetic field alone may be weak. The host galaxy alone may be forming stars according to familiar gravitational rules. When they come together under the right conditions, the result is a quasar, a state in which the center of a galaxy becomes bright enough to outshine the galaxy, energetic enough to heat its fuel, and persistent enough to affect future generations of stars. This relationship depends on imbalance. Matter wants to fall inward. Radiation pushes outward. Rotation prevents direct collapse. Magnetic fields redirect motion. The disk feeds the black hole while the black hole environment disrupts the disk. The engine works because opposing tendencies do not cancel perfectly. They create a channel through which energy can keep moving. That also means quasar strength is never absolute in a simple, static way. A quasar can fade when fuel runs low. A jet can weaken when the magnetic structure changes. A galaxy can pass out of its active phase and carry only fossil bubbles as memory. The strength is episodic, conditional, and shaped by supply. Yet this does not diminish it. It makes it more realistic and more profound. The strongest natural engines are not exempt from limits. They reveal their strength by operating near them. The Eddington balance, the availability of gas, the stability of the disk, the alignment of magnetic fields, and the growth history of the black hole all constrain the system. A quasar is powerful not because it ignores those constraints, but because it reaches extraordinary output while still obeying them. It shows what known physics can do when mass, time, and environment are arranged in an extreme configuration. From Earth, the result often returns to the form that began the mystery a point. Even the mightiest quasar may arrive in an instrument as a tiny source of light or radio emission, a compact signal holding the history of a galaxy's active core. That small appearance is not an error. It is the final compression of the journey. Light from a remote engine crosses expanding space, loses intensity with distance, shifts toward longer wavelengths, and still remains detectable. The signal becomes delicate by the time it arrives, but its origin was not delicate. Behind it lay a disk hotter than ordinary starlight, a black hole of immense mass, gas moving at severe speeds, and perhaps jets carrying particles across spaces larger than the galaxy itself. The strongest thing the universe can create can arrive as something nearly fragile in the data. Its strength has to be reconstructed from distance, redshift, brightness, variability, spectra, and the scars left in surrounding gas. In that reconstruction, quasars become more than spectacular objects. They become measures of cosmic possibility. They show that the universe can build engines from darkness without making darkness shine. They show that gravity can become luminosity without breaking its own rules. They show that a galaxy's center can influence its outskirts, its future star formation, and even the temperature of gas beyond the galaxy. They also show that power is not always loud at the place where it is received. It may be quiet in the telescope, faint after billions of years of travel, and still point back to a source that once overwhelmed its own galaxy. If strength means endurance joined to influence, if it means the ability to convert matter into lasting consequence, then the quasar stands as one of the universe's most complete answers, not a solid wall against force, but a sustained engine through which gravity becomes light, and light becomes history. The Milky Way is quiet now, but quiet does not mean finished. At its center, Sagittarius. A star rests in a low feed-in state, surrounded by stars, gas, dust, and old traces of violence that no longer rise to the level of a quasar. The galaxy turns around it without seeming governed by its light. The sun moves far from the center, in a calmer district of the disk, and the night sky gives no visible sign that a supermassive black hole lies behind the dust of Sagittarius. Yet the future of the Milky Way contains a disturbance large enough to change that condition. Andromeda is already approaching. Across the space between the two great spiral galaxies, gravity has begun the slow work that expansion cannot undo at this local scale. In several billion years, the Milky Way and Andromeda will no longer be separate islands. Their halos will overlap more deeply. Their stars will pass through one another's immense volumes. Their gas will be stretched, compressed, shocked, and redirected. And the two central black holes will begin a long inward journey toward a shared core. This does not mean the night will suddenly become a storm of stellar collisions. Stars are small compared with the distances between them, so most will pass through the merger without striking another star directly. The violence belongs less to individual impacts and more to gravity acting on whole systems. Spiral arms will distort, streams of stars will be pulled into long arcs, gas clouds, much larger and more diffuse than stars, will collide and lose energy. That gas will matter most for any future awakening, because a black hole cannot become a quasar without fuel. The merger will disturb reservoirs that have spent long ages orbiting more quietly. Some material will be thrown outward into tidal tails, some will be heated and prevented from collapsing, but some will lose angular momentum and begin sinking inward, toward the growing central concentration where the two galaxies are being remade. In that inward drift lies the possible return of quasar physics to the local story. A galaxy merger is not only a collision of stars, it is a rearrangement of pathways. Gas that once remained spread through a disk can be torqued by changing gravitational fields, pulled out of its previous orbit and driven toward the center. Bars, shocks, and tidal disturbances can all help remove angular momentum. As the inflow strengthens, the central region becomes denser, warmer, and more chaotic. Star formation may surge as clouds compress. Massive stars may ignite and die in rapid sequence, enriching and disturbing the gas around them. At the same time, some of that material may continue past the stellar nurseries and approach the supermassive black holes. Andromeda has its own central black hole. Sagittarius, a star, has the Milky Ways. As the galaxies merge, their black holes will eventually become part of the same remnant galaxy, drawn inward by interactions with stars, gas, and dark matter. The final black hole may be more massive than either one alone, and if enough gas reaches its surroundings, the new core could brighten into an active galactic nucleus. Whether it becomes a true quasar depends on details that cannot be known with certainty from so far in advance. The gas supply may be too depleted by then. Feedback from star formation may heat or expel some of the fuel. The geometry of the inflow may be irregular. The final black hole's spin and magnetic environment may not favour the most powerful jets, yet the ingredients for renewed activity are clear. A large merger can drive gas inward. A central black hole will be waiting. The same laws that power distant quasars will remain available. If the feeding rate becomes high enough, the quiet centre of the future merged galaxy could ignite, not as a new principle, but as an old engine returning to work under fresh conditions. The scale of that future is difficult to hold because it lies beyond the present age of the Sun as a stable star. By the time the Milky Way and Andromeda are deep in their merger, the solar system itself will be in a changed era. The Sun will have grown brighter over its long main sequence life, and later it will swell toward its red giant phase. Earth's surface conditions will no longer resemble the world that first learned to study quasars. The future awakening of the galactic core is therefore not a direct human hazard in any ordinary sense. It belongs to a time so remote that the local meaning of habitability, planets, and civilizations may have changed beyond recognition, but as a cosmic continuation, it is profound. The same galaxy that now carries a quiet black hole and a living planet around an ordinary star may one day become part of a larger elliptical remnant, with a central engine stirred by the remains of two spirals. What is dormant now may not be dormant forever. The possibility also reframes the distant quasars. They are not only strange objects from unreachable history, they may be glimpses of phases that many galaxies experience when conditions become favourable. A galaxy can be calm for long intervals, then active, then calm again. Its central black hole can spend most of its existence in hunger, punctuated by episodes of feeding intense enough to affect the entire host. The Milky Way's future merger with Andromeda is one more turn in that cycle, though on a timescale far beyond human planning. If the new core lights strongly, radiation from the accretion disk could flood the central regions. Winds could move through gas already unsettled by the merger. Jets, if they form, could cut outward along the spin axis of the black hole and deposit energy into the surrounding halo. Star formation could be first encouraged by compression and then limited by heat. The same feedback loop described in distant galaxies could unfold close to home. In the descendant of the Milky Way itself, this is not a prediction of a guaranteed beacon, it is a recognition that the physics is waiting. The central engine does not vanish during quiet eras, it only lacks the sustained inflow needed to reveal its full strength. Sagittarius. A star today is a faint reminder of that distinction. It shows that a black hole can dominate local orbits while remaining dim. The early universe shows the opposite condition, when gas-rich galaxies fed their centers so vigorously that quasars became common across great distances. The future merger offers a bridge between the two. It suggests that cosmic strength is episodic, not because the laws change, but because environments change. Fuel is gathered, spent, heated, scattered, and sometimes returned. Galaxies grow by encounters, and encounters remake their centers. A quasar is one possible outcome when the timing, mass, gas, and geometry align. The strongest thing the universe can create therefore has no need to be permanent to be decisive. It may sleep through most of a galaxy's life and still alter that galaxy during the intervals when it wakes. There is a quiet symmetry in this ending. The mystery began with distant points. signals from a younger universe that looked small only because they had travelled so far. It turned inward to the Milky Way, where a central black hole proved that the same kind of engine could exist nearby in a subdued state. It then widened again, toward the future, where the Milky Way's calm centre may be disturbed by a merger already written into the motion of the local group. Across that arc, the quasar becomes less like an isolated monster and more like a phase of galactic life, rare at any given nearby moment but central to the history of structure. Its strength lies not only in brightness, but in return. Matter falls inward. Energy moves outward. The host galaxy changes. The fuel supply shifts. The engine fades. Then, after long silence, another disturbance may begin the sequence again. If Sagittarius, a star, ever awakens into something approaching a quasar, it will not be a surprise in the deep physical sense. It will be the universe repeating one of its most powerful arrangements: darkness at the centre, matter in descent, magnetic fields in tension, and light strong enough to make a galaxy's own stars seem secondary. For now, the Milky Way remains quiet, and its black hole is a shadow with only a faint surrounding glow. But the future carries motion, and motion carries consequence. The sleeper at the centre does not need to dream, it only needs fuel. In the end, the strongest thing the universe creates is not only an object, and not only an event, it is an arrangement of matter, gravity, time, and motion brought into a narrow balance at the centre of a galaxy. A quasar begins with darkness, but it is not defined by darkness alone. It becomes visible through everything that cannot enter quietly, gas forced into orbit, plasma heated by descent, magnetic fields wound into tension, radiation escaping before the final boundary is crossed. Its power is severe, yet its meaning is not only destruction, it marks the way galaxies feed, regulate themselves, and carry the memory of their most active ages. Some quasars shine from a universe so young that their existence still feels almost too early. Some black holes sleep inside nearby galaxies, holding the same possibility in a quieter form. Between those states lies the long rhythm of cosmic structure, where fuel gathers, centers awaken, energy spreads outward, and silence eventually returns. The mystery remains because the evidence has edges but not complete closure. The engines are known, but their first seeds are still uncertain. Their effects are visible, but their full histories are difficult to recover. Their strength can be measured in light, in jets, in heated gas, and in the futures of galaxies that form fewer stars because a hidden centre once burned too brightly. This is a calmer kind of awe, not a single flash, but a process patient enough to shape deep time. The universe does not need to be loud to be powerful. Sometimes its greatest force arrives as a faint point of ancient light, carrying the record of a dark engine that turned falling matter into history.